Hello guys, welcome back to TechDose, and in this video we will see the box stacking problem, which is from dynamic programming, and this is a variation of longest increasing subsequence. So a prerequisite for solving this problem is knowing all about the longest increasing subsequence. I have already uploaded this video in my DP playlist, so you can watch that and the link will be present in the description below. Now coming to this problem, we will be given n number of 3D rectangular boxes which you may assume to be a cuboid, n number of cuboids, and the dimensions will be height, width and length. Okay, our goal is to create a stack of boxes as tall as possible, but we are given certain number of constraints. So these are the three constraints. The first one is one box can be stacked on another only if the lower box has strictly higher dimensions. The second constraint is rotation of a box is allowed, and the third constraint is multiple instances of same type of boxes are allowed. Now this is a diagrammatic representation of a box. Here it will be just like a cuboid where you will be having height, width and length, and the dimension format will be HWL, right? So before solving this problem, before looking at any example, let us first understand about these three constraints in detail, because these are very important for solving this problem. Now coming to the first constraint, the first constraint was that one box can be stacked on another only if the lower box has strictly higher dimensions. So what does that mean? In this example, you might think that if you have a base area, let's say you are having base area B1 and you are having base area B2, then according to the first constraint, you might think that if base area B1 is greater than base area B2, then you can fit the box 2 on top of this box 1. Okay, so this is box 1 and this is box 2. So this may not always be true, right? Because if you are having some peculiar shape, let us assume that this is base area 1. This entire thing is base area 1. Here length 1 is very larger than this length 2. And this width 1 is very small, that like it is smaller than this width 2, right? So L1 is very larger than L2, and width 1 is less than W2. So in this type of cases, you will find that L1 W1 will be larger than L2 W2. But this doesn't mean that you can fit this base area B2 on top of base area B1, because this base area B1 is very thin. If you put this B2 on this B1, then it will go out in this part and in this part, right? So you cannot fit them. According to the constraint, it is saying that one box can be stacked on another only if the lower box has strictly higher dimensions. These higher dimensions doesn't refer to area, but it refers to the dimensions which are used to calculate the base area. So it is referring to this length and width. So strictly lower dimension means if you want to fit this B2 on top of B1, then L2 should be less than this L1, and also W2 should be less than W1. If this case is true, this is called strictly lower dimensions, right? So if this is the case, then only you can place this box 2 on top of box 1. So if you look at this second example, then here you can see that this W1 and L1 is taken, but W2 is less than W1 and also L2 is less than L1. Therefore, this box with base area B2 will obviously be less than this B1, because both the dimensions are lower. And so since the individual dimensions, the corresponding individual dimensions are also lower, so you will be able to place this B2 on top of B1. Okay, so this is the case, like we need to compare both the width as well as length. We don't just want to compare the area. Therefore we can't compare on the basis of area. This you might have understood by now. The second constraint is that rotation of the boxes are allowed. Now what does that mean? In this case, this is one box. Okay, now how do you rotate it in order to produce some unique boxes? Because producing the same box will not be beneficial for us. Like in the previous case, I already told you that strictly means this W2 should be less than W1. Now if you are making the same boxes multiple times, then also there will be no benefit, because the boxes having the same dimensions cannot be put on top of it, because it needs to be strictly decreasing. Okay, the dimensions needs to be strictly lower than the dimension of the base box. So if you make multiple copies of the same boxes, then you cannot put them on top of one another, right? Therefore, you need to make unique rotations. So a cuboid is basically 6-faced and there are 3 pair of surfaces having equal area, right? Now you cannot rotate it 180 degrees because that will form the same dimension, because the opposite pairs will be equal. Okay, the top and the bottom are equal, right and left are equal, like that. So we will be rotating it 90 degrees. So once you rotate 90 degrees to the right hand side, then you can see that I have marked the dimension here. Length will remain at the same position. Height will be replaced with this width. Okay, you can try this and you will understand. The same goes for this one. If you rotate 90 degrees to the left, then you will find that its dimension will change like this. So these are the possible rotations of a box. This is one box, this is the same box. So by using a box, we can form 2 other unique rotations. So if we are given one box having different L, W and H, then we can have maximum of 3 unique boxes, right? So our purpose for rotation is to generate new cuboid configurations. Rotating a cuboid by 180 degrees will give same configuration, and therefore only 3 unique cuboids can be formed. I hope you understood this second constraint. The third constraint said that we can have multiple instances. Okay. Now, as I already said, if you are having a box, then you will not be taking the same box multiple times, because that will not increase your height, because according to the question constraint, the height should be strictly decreasing. That is, if there is one box, then the other box which lies above it should have strictly lower dimensions, both in terms of length and width, right? So you cannot take equal length and width. So if it is not contributing to increasing your height, so we will not be forming the same boxes again and again. Therefore, we will try to form unique boxes. And since I have already explained that if you are having a box, then using 2 rotations, you can form 2 other unique combinations. Okay, 2 other unique boxes. Therefore, if you are given a box, then you can form a total of 3 unique boxes. So any given box can form 3 unique cuboids by rotation. Therefore, a given instance of box can be included maximum 3 times using rotation and can be used to stack one on top of the other, right? So this is the case for multiple instances. Therefore, if you are having, let's say, n boxes, then using this property of multiple instances, you can have maximum of 3n number of unique boxes by using rotation. Okay, so I hope you understood this point as well. Now, having understood all the constraints, let us now look at an observation. In this case, if you look at this example, we are given 3 boxes having these dimensions, which is in format of height, width and length. Now the maximum stack height which we can form by putting one box on top of the other will be 56. Now you can see here that we are having just 3 boxes, and even if we add the maximum values from all these 3 boxes, it will not reach to 56. So how has this come? Now, as I already told you, you can use rotation. For this box, you can use rotation and you can form something like 12, 10, 32, right? And you can also form other combinations like 32, 10, 12. So these 2 combinations are also formed from this box. So a single box will be contributing to 3 boxes, this 1 box, 2 box and this box itself, 3 boxes. So here we are given 3 boxes, so total there will be 9 number of boxes. If you take those 9 number of boxes and stack in such a way that you pick some of those boxes, let's say you pick k number of boxes out of this n number of boxes, and you put those k boxes one on top of the other such that it forms something like a pyramid structure, then the boxes will be strictly decreasing dimension. Okay, the base box will be of highest dimension. Therefore, this is the maximum height which you can form, and this we need to calculate. Now in this case, the maximum height which can be formed is 56, and the first configuration to form this height 56 is if you put this 10, 12 and 32 at the base, because this is having the highest area and also the highest strict dimensions based on L and W, right? Now you can put this second last one on top of this one because this is having the second largest area and also the second best strictly decreasing dimensions, right? So in this way, we will put all these elements in decreasing order of area, and then we can find that this one will be giving you the maximum stack height. There is still another configuration. You can see that this is one another configuration which will be giving you the maximum height if you add these values, height values. Okay, so here, since two configurations are giving you the maximum height, it doesn't matter. We are just concerned about what is the maximum height. We can also return the configuration. The question might be changed so that you are asked to also find the configuration. That is very easy. It is the same as finding the longest increasing subsequence configuration, right? So even if there are two other configurations, let's say this first configuration height was, let's say it was using only 5 boxes, and this second configuration was using 7 boxes, and they both were giving you 56. It doesn't matter, because you are just concerned about the height and not about the number of boxes being used. So number of boxes are irrelevant in this case. So we just want to maximize the height, and the number of boxes used for maximum height doesn't matter. And if two or more configurations have maximum height, we don't care. We just want to return the maximum height, right? Let us now look at an example and understand the intuition for solving this problem. Let us assume that we are given these 3 boxes. Now since we are allowed rotation, we can form maximum of 9 number of boxes which will be unique out from these 3 boxes, because one box can form maximum of 3 unique boxes, right? So we will be producing all the rotations, and therefore the box instances are created. So this is step number 1, and this I have already done here. Now if we want to create a pyramid like structure by stacking one box over the other, let's say there are many boxes stacked one over the other. Let's assume that this is box 1 and this is box 2. Then obviously this base box will be having the highest area, both in terms of area and also in terms of strict dimensions. That is, if you take L1 and W1, then L1 will be greater than L2 and W1 will be greater than W2. Okay, this is what strict dimensions mean, strictly decreasing dimension. So this will always be true, right? So what we will do is, we will be sorting all these boxes based on the base areas, okay? Because the lower one will obviously be having the highest area. So we will first be considering only the area and not these dimensions. This we can use later on while solving this problem. So this is very intuitive that you can form 9 rotations. So we have formed these combinations, and then we will be sorting it based on the area. So let us sort it based on the decreasing area. You can also sort based on ascending order of the area. So our second step is we need to make a pyramid like structure. Therefore boxes must be arranged in ascending or descending order based on the base area, so as to form the largest pyramid possible. Therefore we will sort the boxes in ascending or descending order of the base area. Okay, so let me just give you a pictorial representation of what we are thinking about. So let us assume that this is only the width. Okay, now in terms of width, if we have arranged the entire boxes in terms of area such that this is the highest area, this is highest, and this is the lowest area, right? So even though this is the highest area and this is the lowest area, in between there can be some peculiar dimensions such that the width is more but the length will be less. Okay, so let's assume that this is one width is given but the length is low. Okay, and this one which is lying below it, this part, this is having a given width and this might be having a given length, right? So this area is more, therefore this will be lying below this one. Okay, so that is how we have arranged. We have just arranged based on the area. So after sorting we can get something like this. Okay, so here we are just seeing the width. Now what we will do is we have just arranged based on the area, but now we want based on the strict ordering of L and W. Okay, that is the dimensions of the area. So we will be removing all those boxes which cannot be stacked one on top of the other in order to form a pyramid. So a pyramid should be strictly decreasing, okay, both in terms of area as well as in terms of L and W. So if L1 is less than this L2 and W1 is less than W2, then obviously L1 W1 will be less than L2 W2. So we don't need to check the area, we just need to check this L1 and W1. Okay, so we will be removing these unnecessary boxes, and after skipping these boxes we will be forming the highest pyramid which will be possible. So the things to note here is, if B1 is less than B2, then it doesn't guarantee that W1 is less than W2 or L1 is less than L2. This I had already explained in the constraint part, okay? Because one dimension may be very large than the other, making the base area more, but both the dimensions must be less, okay? So we will be skipping some of these boxes in order to form the longest decreasing boxes in terms of area and strictly in terms of L and W. Okay, so I hope you understood this point. So how do we solve this problem? Actually, finding the highest stack is same as finding the longest decreasing or increasing subsequence. So in this case, what we were doing is we were finding the longest decreasing subsequence if you see from bottom to top, and if you see from top to down, then we are finding the longest increasing subsequence, right? Because those sequences will be skipping all these points. So that is nothing but the LIS problem, longest increasing subsequence. So just to recap, what we did in this entire problem is, first we will produce all the rotations and we will form all the configurations. Second thing is sort them based on area. You can sort in ascending or descending order. I have done in descending order. Now after doing that, you will get something like this figure, and then you can find the longest increasing subsequence if you move from top to down like this, or if you move from bottom to up, then you can find the longest decreasing subsequence. So this is the third step. That will give you the maximum height which you can form by stacking one box on top of the other according to the given constraints. Okay, so I hope you were able to understand the entire intuition behind the problem. Now let us see a dry run. So before seeing the dry run, we will be storing the cuboid dimensions in a structure named as box, and we will be storing in forms of height, width and length. Okay, so let us look at an example and understand this entire problem. So I have taken the previous example and I have formed all the rotations which are possible. So in this problem, we will be starting from this first point. This is our I pointer and our J pointer will be at 0. Okay, this is the same as the LIS problem, longest increasing subsequence. So you can watch my video on that and then come back in order to get this full understanding. Now in this case, the condition will be like, if you are at this ith pointer and you want to find the longest decreasing subsequence in this case, so the ith box width should be less than the jth box width, and also the ith box length should be less than the jth box length. Okay, because you want to find the decreasing order of the boxes. And when these dimensions are strictly lower, then the third thing you need to check is, if you include the given box at this ith point, then that will lead to a longest decreasing subsequence. Okay, so this is the case which is also common with the longest increasing subsequence problem. So if the height which you have formed at I till now is less than the height which you got at J plus the current box height, which is the ith box height, then you will update this longest decreasing subsequence at I with the longest decreasing subsequence at J plus the current height of I. Now why do I keep saying subsequence? Because in this case you can see that we had formed this pyramid by skipping some of the boxes in between. So this is the concept of subsequence. Between any two characters you can skip any number of characters. You can also skip any number on the left side, you can also skip any number on the right side. This is the concept for subsequence, and the same goes for this one. You can skip the boxes anywhere, right? So let us now move on to the dry run. Now in this case the boxes are numbered like 0, 1, 2 and so on. This is 3, 4, 5, 6, 7, 8. Now when you are looking at this box 0, then obviously this is having width equals to 32, length equals to 12, and this one is having width equals to 32 and length equals to 10. So this is not strictly decreasing because these two are equal, so it will not get updated. Now I will get updated to the next value and J will again start from 0. Now we will update it. Now we are pointing to this point 2. So if we look at this box 0, then 32 is larger than 12 and 12 is larger than 10. Therefore this is a decreasing sequence, right? Dimensions as compared to this one, right? So this box 2 can be stacked on top of box 0. So box 0 is having height equals to 10 and box 2 is having height equals to 32, right? So if you stack them on top of the other, then will this give you a better height? That means will this increase your height of the stack? Now you can see that 10 plus 32 will be greater than 32, and so it will increase your height. So we will be replacing it by a value 42. This is according to this one, right? Now we will be moving to the next point, which is this one. So for this second point, you can see that 32 is greater than 12, but 10 is equals to 10, so they are not strictly decreasing, so we will not be doing anything. So we will update the I pointer, it will go to point 3. Now we are pointing to this box 3. We will again be starting our J pointer from this point 0. Now this 32 is greater than 7, 12 is greater than 6, so it is strictly decreasing dimension. And so if you look at this point, then if you add this box's height, longest decreasing subsequence at this point J with this height 4, then will this be more than 4? Yes, it will be more than 4. So we need to update it. It will be 14, right? Now we will move on to the next point. We will be pointing to this point, this box 1. 32 is greater than 7 and 10 is greater than 6. So again it is strictly decreasing. Again we will check 12 plus whatever the height is at 3, which is this 4. 12 plus 4 is greater than 14. So this will again be updated and this will become 16, right? Now we will again be moving to the next point. This is point 2. Now point 2 is having 12 as dimension, 10 as dimension. This is 7 and 6. So this is strictly decreasing. Now the height at 2 is 42. Okay. And the height of this box 3 is 4. So 42 plus 4 is 46. But the height as 3 is 16. So 46 is greater. Therefore we will be replacing here 46. Okay. Now all the points have been traversed. We will now increment our pointer. We will be pointing to this fourth box. Okay. So this fourth box is having height equals to 4, width and length as 6 and 5. Now we are at this box 0 again. Box 0 is having 32 and 12. This is having 6 and 5. So this is strictly decreasing. Now if we add this 10 to this current height 4, which will be 14. Is it greater than 4? Yes, it is greater than 4. We will be writing 14 here. Now we will be moving our pointer to this point. We are pointing to this first box. 32, 10 is greater than 6, 5. We will again be updating it if and only if this 12 plus the current height 4, which will be 16, is greater than this height, which is the longest decreasing subsequence at point I, which is 14. Yes, 16 is greater, so it will be replaced with value 16. Now we will see the next point, which is this point 2. Now point 2 is having 12, 10 and this is having 6, 5. So this is strictly decreasing. Now height at 2 is 42 plus the current height is 4. Is 46 greater than the longest decreasing subsequence till now found at point I 16? Yes. So we'll update it to 46, right? And we will move on to the next point, which is this 46. This third point. So 7, 6 is greater than 6, 5. This is strictly decreasing. Therefore we will again check this third index height is 46. Okay. And if we add this current index height, which is 4, to this one, then it will be 50. So 50 is greater than 46. We will replace it with 50. Okay. So all these points have been traversed. So we will now move on to the next point. It is point number 5. We are moving to this point 5. Again we will start our J pointer with this one 0. And again this 32, 12 is greater than 7, 4. So we will check if 10 like this one, if 10 plus this 6, 16 is greater than this 6. Yes. So we will replace it with 16. Again move on to the next point. This one 32, 10 is greater than 7, 4. So again 12 plus 6, 18 will be greater than this 16. Yes. So replace it here. Move on to the next point. Again this 12 plus 10 and this is 7, 4. So this is strictly decreasing. Now this 42 plus this 6, which will be 48, greater than 18. Yes. So replace it with 48, right? Move to the next point. Now at this point 3, this is 7, this is 6, it is 7 and 4. So 7 is common and therefore it is not strictly decreasing. So we won't do anything. Move on to the next point, index 4. So at index 4, this is 6, 5 and this is 7, 4. It is not strictly decreasing because 6 is lower here. So we won't do anything and all the points have been traversed. Now we will move on to the next point. We will move to point 6. Okay. Now again we will be starting with this point 0. So this 32 and 12 is greater than this 6 and 4. Again we will check this 10 plus this 5, 15 is greater than whatever the value is at 5. Yes, we will write here 15. Move on to the next point. Now 32 and 10 is greater than this 6 and 4. So 12 plus 5, is it greater than this 15? Yes. So it will be replaced with 17, which is 12 plus 5. Move on to the next point. This is point 2. 12, 10 is greater than this 6, 4. Okay. And the value here is 42. 42 plus 5, which is 47, is greater than 17. Yes, we will write here 47. Move to the next point. We are at this index 3. 7, 6 is greater than 6, 4. Yes. So we will check if 46 plus this 5, that is the longest decreasing subsequence at point J, plus this current height of the box 5, that is 51, is greater than the currently found longest decreasing subsequence at point I, which is 47. Yes, 51 is higher, we will replace here. Move to the next point, point 4. 6 and 5, and this is 6 and 4, so this is not strictly decreasing. Move on to the next point, which is 5. 7 and 4, this is 6 and 4. This is not strictly decreasing, we won't do anything, right? So all these points have been traversed. Now we will move on to the next point, which is point 7. Now we are at point 7. Again we will be starting with this point 0. This 32 and 12 is greater than 6 and 4. Again this 10 plus this 7, that is 17, is greater than this 7. We will replace here with 17. Move on to the next point. 32 and 10 is greater than 6 and 4. So 12 plus this 7, which is 19, is greater than 17. Right here 19. Move to the next point. 12 and 10, this is 6 and 4. So this 42 plus this 7 will be equals to 49. So 49 is greater than 19. Right here 49. Move to the next point. We are at point 3. 7, 6 is greater than 6, 4. Right. So is this 46 plus this 7, which is equals to what? 46 plus 4 is 50. 50 plus 2 is 52. But this will be 53, right? So 53 is greater than 49. Yes, right here 53. So this is 53 basically. I hope you are understanding it. Now we move on to the next point. This is point 4. So point 4 is having this dimension 6 and 5, and this is having 6 and 4. So this is not strictly decreasing. Now if you check this point 5 as well, it will not be strictly decreasing. Point 6 will also not be strictly decreasing. So this will all be done. Move on to the next point, which is point 8. So at point 8, we will again be starting from point 0. Right. This is very hectic, so please keep up with us. 32 and 12 is greater than 5 and 4. So we will check if 10 plus 6, 16 is greater than this 6. Yes, 16 will be updated here. Move on to the next point. So we are at point 1. 32, 10 is greater than 5, 4. So it will again get updated if 12 plus 6 is greater than 16. Yes, we will be updating it with 18. Now we are at this index 2. So 12 and 10, and this is 5 and 4, strictly decreasing. Now this 42 plus 6, which is 48, is greater than 18. Yes, we will write here 48. Move to the next point. Now here this is index 3, right? So at index 3, this is 46. Now first we will be checking the dimension, obviously. 7 and 6, and this is 5 and 4. Yes, strictly decreasing. So 46 plus 6, which is equals to 52, is greater than this 48. So we will write here 52. Okay, now move on to the next point. Now at this point 4, this is 6 and 5, this is 5 and 4. So strictly decreasing. Now at this point we are having this value 50. Okay, so 50 plus 6, which is 56, is greater than 52. So we will write here 56. Now move on to the next point. We are at this index 5, 7 and 4, and this is 5 and 4. So it will not be strictly decreasing, and all the further points will not be strictly decreasing. So we can stop here. Now what we will do is, our array is filled with values 10, 12, 42, 46, 50, 48, 51, 53 and 56, right? These are the values. Now we will be picking the maximum value by traversing this array once. So this is the maximum value, which is 56. Okay, it may not be presented at the last position. We need to traverse it. So this will be the longest decreasing subsequence, or you can say the longest increasing subsequence. So this is how we can calculate the maximum height, that is the maximum stacking height of all the boxes according to the given constraint in this problem. So this problem is similar to finding the LIS, and the time complexity will be order of n square because this is the most time taking process which is for calculating the LIS. Now here there is one thing to notice. Let us say that you are having H, W and L, okay, and you are having values here. Let's say this is 10, this is 12 and this is, let's say, 15. And let's say you are having a second box having height equals to 9 and your width is equals to 13 and your length is equals to, let's say, 9, right? So in this case you can see that this box 1 and this box 2 will not be strictly decreasing, because if you compare these values, this is 12 and this is 13 and this is 15 and this is 9. So this 13 is greater than 12. So you cannot put this box 2 on top of box 1. But since you are allowed rotation, therefore what we can do is we can rearrange these values so that you will be comparing the maximum dimension with the maximum dimension of the corresponding box, right? So in this case we should not compare this 13 with 12, but instead we should compare with 13 with the maximum value of this box. So the maximum dimension of box 1 should be compared against the maximum dimension of box 2, right? And the minimum dimension of box 1 will be compared against the minimum dimension of box 2. So this is one logic which is very important for solving this problem. This you might have missed, right? So here this 13 should be compared against 15. So how do we take care of that? Well, in this case height will only be added in your LIS calculation, that is in your longest increasing subsequence calculation. But this is your condition for checking. So you are having two values. So what we can do is we can set that, like we can assume that we will be keeping the maximum value of the dimension of L and W in your W, and you will be picking the minimum value in your L, okay? So if you take the maximum of 12 and 15, then after rearrangement 15 will come here and 12 will go here, right? And in this part as well, after rearrangement this 13 will be at the same position and 9 will be at this position, right? So in this way, if you fix that the maximum dimension, leaving this height part, obviously the maximum dimension will be present in W, minimum will be present in L, because there are only two dimensions. Then if you keep this throughout the dimensions, that is throughout all the boxes, then we can simply compare W1 with W2, right? And we can find out if this is greater or that is greater. So this is the correct way of comparison for this problem. If you do not follow this, then this problem will be giving you the wrong answer. Now let us look at the code. So I think after all these explanations you do not actually need the code, but still I am showing you this. This is basically the driver function. This I have done in Geeks for Geeks. You can also go there and practice. This is the driver function there. Now the driver function will just be taking the inputs and it will be calling the function, right? So this is the code which we have written. Now in this case, this is the box which will be keeping all the dimensions. So we will be making an array of structure. This will be keeping track of all the box dimensions, okay? Now this is the compare function for arranging all the boxes in decreasing order of the area. So this is decreasing order of area. Now this is the main function, which is the max height. Now here we are given the height array, width array and the length array along with the number of boxes n. Now since we are given n number of boxes, therefore we can form 3n number of total orientations, right? So these will be the total unique boxes. So our length will be equals to 3n. We will be taking an array and again we will be taking an index value equals to 0. So for all the n values, okay, if you take the first box, then you will be having 3 unique combinations. So we will be updating the index. So index 0, 1 and 2 will be filled with the first box orientations. Now for the second box we will be filling index 3, 4 and 5, right? So this is how we will keep on filling. Now after filling all the boxes, like this is step 1, that is finding all the orientations. For n boxes you will have 3n orientations. This is step 1. Now after doing step 1, we will move on to step 2. Step 2 was arranging all the orientations in decreasing order. You can also do it in increasing order and find the longest increasing subsequence. I have done in decreasing order using this compare function. This compare function will be taking use of the area, that is the base area. Now after following this step 2, the third step is to find the longest increasing subsequence. Once we have filled the array as I had shown in the dry run, we will have to traverse this array and find the maximum value. So this part is doing that, and then we will return the maximum value, which is the longest decreasing subsequence value in this case. So you can see that this is a simple problem, but this is having so many constraints and so many observations. So you should be watchful for that. Now in this code, I have taken this maximum of length and width in the width part and minimum of length and width in this index part, right? So this reasoning I already explained you why, because we want to compare the maximum value of one base area with the maximum value of the other base area. This is the reason. So I hope you were able to understand this entire explanation. This was a long explanation, but I hope you understood it. If you have any doubt, then feel free to comment below and I'll try to help you as soon as possible. Like and share our video and subscribe to our channel in order to watch more of these programming videos. See you in our next video. Thank you.